Welcome everybody to the latest in our Bridge webinar series. As many of you may know and have come to some of our webinar series before, the Bridge webinar series is a joint venture between McGill University's the Pittsburgh Supercomputing Center and the Johns Hopkins Bloomberg School of Public Health. And we are bringing a number of speakers, a series of speakers in to talk about how the interaction at the interface between brain to society and understanding how behavioral modeling, computational modeling, computational science can all be brought together to bear to understand how we model societal behavior and aspects. So welcome everybody. And I would ask you to please, if you're not going to speak, if you're not the speaker, to please mute just so that we don't have background noise. And if you have a question during the talk, you can either unmute and ask, or you can put into the chat window down below that you have a question. And so then, without further ado, I will turn the program over to Laurette Dubé, who will introduce our speaker.
Thank you, Sean. Good morning or good afternoon, everybody, depending on where you are. I'm very pleased to welcome my Montreal colleague, Michel Gendreau, to whom I have asked to talk about Metaheuristic, which so far he has been applying in addressing problems or challenge more on the economic aspects of life. And as we are looking at helping improve individual and collective choice toward more convergence between what we do on the health or on the social and on the economic, a lot of facets of this meta-heuristic approach in terms of localized effects having global impact, in terms of multi-level source of influence and outcome, as well as diversity and sometimes conflicts between the various goals that those systems are trying to achieve, whether it is transportation, logistics, or whether it is in many ways food or health system. So it is, I would like briefly to give you an overview of this very prestigious academic profile before shifting to him to tell you more effectively than me what is metaheuristic and how it can help the various domains within which each of us is working. So Michel is the department chair and professor of operation research at the Department of Mathematics and Industrial Engineering at Polytechnique in Montreal. He has published more than 300 papers in peer-reviewed journal and conference proceedings. His work is very much about the application of operation research and other and optimization methods for transportation and logistics. He is also a co-editor on many very high-level journals in the discipline. And he was elected Fellow of the Informed Society in 2010. 2015 received the prestigious Robert Herman Lifetime Award for the transportation, science, and logistics. In addition, Michel is a wonderful person and colleague to learn from, and I'm very pleased to welcome you, Michel, and I'm shifting to you for your presentation.
Okay, thank you, Laurette, for the kind introduction. So the topic of the day is metaheuristics. So it's very much oriented towards solving problems and to better understand exactly what we're dealing with. So let me just show you the presentation outline. So I'll briefly introduce the topics, and then I will describe two broad families of methods. I'll just talk also about some recent trends in metaheuristics. And then just before concluding, I'll have a small moment of, I would say, lack of humility to just show you some of the very recent work we've been doing and some very successful application of metaheuristics. So let me first introduce the topic, and I think the right way to begin is by looking at combinatorial optimization. Really, the topic that we're dealing with is those difficult problems when we are trying to optimize decisions that are discrete in nature. And an example of this would be if I'm trying to organize delivery routes. Well, for example, in which sequence should I be visiting customers? Or maybe a simple thing, how many trucks should I buy to be able to service a set of customers? Or in a totally different area, for example, if we're looking at personal scheduling, for example, on what shifts should this nurse work on and on which days should she be off. So that's the general nature of the problems that has been our concern and is a concern of a large fraction of the community in operations research and optimization. Those are difficult problems that have fascinated people since quite a long time, because you can find occurrences of combinatorial optimization problems going back to 19th century and even before. One of them being, for example, a traveling salesman problem that has been a topic for curiosity for quite a bit of time. And one very significant development has been the emergence in the early 1970s of complexity theory. And at that time, people in theoretical computer science came up with this notion of NPhard problems. And this came as a disappointment to many people working in OR because it basically indicated that a number of important problems would not be solved efficiently, in the sense that would not have algorithms that would require a polynomial number of operations when put in relation to their input. However, saying that might have been just nice for people working in the area, so in the sense that, oh, I cannot find a really good algorithm, but it did not detract from the real practical concerns. Is that lots of those problems, if you're looking at lots of problems in transportation and logistics, lots of problems in scheduling, they are combinatorial, they are NP-hard or NP-difficult, and they need to be solved. They need to be solved in practice. So what is the way out? Well, the way out is, in fact, to use what we call heuristic approaches, so approaches that will provide approximate solution. And a typical class of this has been constructive heuristics that have been known for a long time. For example, well-known greedy methods where one typically just asks small questions one at a time and then builds this whole solution from there. And second class has been iterative improvement methods. And what do we mean by those methods? Well, there's a whole thing called classical local improvement heuristics, which rely on a key idea, which is that one would expect good solutions to share similar structures, so that effective solutions should have points in common. And from this idea, one can derive an operating principle, which is to start with an initial solution, usually a feasible solution to the problem, and then to modify this solution over time through a sequence of local modification. And the condition is that each change in the solution should improve it with respect to the value of some objective function. So the way we value the solutions will evolve in a monotonic fashion. And this is very important for technical reasons. And those methods will typically stop when one runs into a solution which cannot be improved, and this is what is called a local optimum. From that point, we cannot get a better solution using the technique. So, in fact, those local improvement heuristics can be seen as basic and trajectory-based search methods. They are the start of this whole thing. So they're also called local search or neighborhood search in the literature. What are the problems and limitations of those techniques? Well, basically the big problem is that they stop when they encounter a local optimum. And with respect to the modifications that one considers. And in fact, the quality of the solution and unfortunately the CPU times, they depend on something that we could call the richness of the set of transformations considered. So if we consider lots of transformation, then this will take a lot of time and hopefully will give us good solutions. On the other hand, if we just consider a limited set, well, we will have a method that will run quickly, but will return most probably not so fantastic solution. So something also that a lot of people did not notice is, until I think fairly recently, is that really a key factor is the definition of the set of solutions that one is looking at. And this we will come back later. So let me now shift to a bit of history. So back in the late 70s, after I would say the emergence of complexity theory, the standard fare of GWAR, with respect to those tough combinatorial problems, is to use a mixture of construction and iterative improvement methods. At the same time, there was some strong interest in artificial intelligence circles, so people more in computer science departments, for developing new problem-solving techniques or search methods. And there was also a strange beast called genetic algorithms that have been proposed back in 1975, but that the operations research community did not care too much about. And then I would say, thunderstruck in 1983, bunch of physicists, Kirkpatrick, Gillick, and Vicky, published a paper in Nature on a thing they called simulated annealing. And what simulated annealing is, it's in fact some probabilistic variant of local search, such that it's capable of overcoming local optima and that it has some proven convergence properties. Now, one has to be very, I would say, sober about those convergence properties. In fact, what they prove in the original paper is that if they were to perform an infinite number of iterations of their method at an infinite number of temperature levels, they would converge to the optimal solution. So that's not such a big thing. But the important element about this paper is that it really shook the OR community. A lot of people who thought that it was nothing more to do than what they knew, local improvement methods, were forced to reconsider their viewpoint on the whole situation. And among others, Fred Glover published in 1986 a very interesting paper, which was about, in fact, the connections between operations research and artificial intelligence. And in this paper, he did two things. He presented a method which he called taboo search, which we will discuss later. And he also coined the concept of metaheuristics. And what are metaheuristics? Well, they're more like general methods, general solution approaches that were designed to control and guide problem-oriented heuristics. So somebody would develop a metaheuristic by using a general strategy and elements that would be really specific to the problem at hand. And in fact, there's been rapid development over the next 30 years. If you look at the literature now on metaheuristics, it's absolutely huge. I have no idea on the total number of papers that have been published on this topic, but it's really, really huge. And for example, if I have co-edited the handbook of metaheuristics, which does not cover everything, and it's about 700 pages long. So that gives an idea of the scope of the topic. So metaheuristics, they are basically two main families of methods. One family is called trajectory-based methods. It includes simulated annealing and taboo search and many others. And then there is a whole different class of methods called population-based methods. So it includes genetic algorithms that I talked about earlier. It also includes like fancy things like ant colony optimization and many others. And in fact, the complete taxonomy of metaheuristics is would take more than the duration of the whole webinar. Mm-hmm. So let's talk about trajectory-based search methods. And the first topic I would like to cover is, I would like to talk about search spaces and neighborhoods, starting with search spaces. So what is the search space of a metaheuristic? Well, it's just, mathematically speaking, the space of all possible solutions that can be considered by the method. So for instance, it can be the set of all the feasible solutions to the problem. So if I'm looking at a problem of optimizing delivery routes, it's all possible routes, all the possible solutions that one could find for this problem. And in fact, each point in the space is associated with a solution that satisfies all the constraints of the problem. Now, this might look like a very natural and straightforward definition, but in fact, one can do different things, and I will show you an example of this later. Now, there's something else which we call neighborhoods, and it's just that when we're doing some local search, the local transformations that can be applied to the current solution, which we call S, will define, in fact, a group, a set of solution, which we call N of S, and this is the neighborhood of S. So by applying a single local modification to the current solution, I will end up to one of the solutions in N of S. And in fact, if we're looking at specific problems, then there are usually lots of possible neighborhood structures that we can define, and usually a lot more than search space definitions. So to illustrate this, and I hope it's not too far from the audience interest, I have two illustrative problems, and the idea is just to try to capture the general sense of this. The details are not important. So a problem on which I've spent a lot of time in my life, which is the classical vehicle routing problem. Basically, we are given a graph that is a set of vertices. Those vertices represent, one of them is the depot, and the others are customers. The arcs between those vertices are just possible moves, and we have the cost or the distance of those moves. At the depot, we suppose that we have a fleet of vehicles that are identical, and basically what we want is to service customers. So each customer has a demand and possibly service time. And what we want is to find delivery routes such that each route starts and ends at the depot. So we imagine the vehicle leaving in the morning from the depot and returning at the end of the day. We want each customer to be serviced by exactly one vehicle. We want to have the total demand of the customers that are assigned to each route to be below the capacity of the vehicle. So we're just imagining that, truck 1 will leave and service customers, let's say 1, 2, 3, 4, 5. Well, we want the total demand of those customers to be below the capacity of that vehicle. And sometimes we also have constraints on the total duration of the route, including travel and service times, which must be below a specified value, for example, the length of the workday. And our objective is really to minimize the total cost of the route. So we're just trying to minimize distribution costs for this set of customers. So this is one of the key problems in logistics. It's been studied for almost 60 years now. There's been thousands of papers written on this problem and its variations. So what about search spaces for this problem? Well, obviously, we could have a very natural definition, which is just a set of feasible routes. But we can do better than, shouldn't say do better. We can go further and consider, for example, routes that will not necessarily meet capacity or duration constraints. And this might be more effective in the solution process. We could also, for example, consider solutions in which some of the customers are not serviced, and in fact, some methods do use this search space, which is a lot more, much larger than the original one. And when we have those search space, well, what would be neighborhoods? Well, we can have neighborhoods that correspond to very simple manipulations of solutions. For example, we could just take one customer from it who is currently in, let's say, route 1 and move him to another route. Or we could move him within the route. and reinsert them in this route. We could decide, for example, that we're going to be swapping customer between routes. So I'm taking customer 15 in route 1 and customer 25 in route 2, and I'm just exchanging them. So now vehicle 1 will service customer 25 and vehicle 2 will service customer 15. We can, in fact, combine some of those things, and this has been proposed back in the early 90s by Ibrahim Osman. We can, in fact, make changes to several routes in combination, and this is called ejection change. Or we can do, for example, swaps of sequences of customers between two routes. So we would take a sequence, let's say, of 3-4 customers in route 1 and exchange it with a sequence of, let's say, 3, 4, 5 customers in another route. So those are all possible neighborhoods for this problem. Okay, let's consider a different problem, the capacitated planification problem. Now, I would like to draw your attention, especially for those who are not so much in the, let's say, economic side of things, that plant here is a very generic word. It's sometimes called capacitated facility location problem. It can be used to locate libraries, hospitals, I don't know, cancer screening centers, whatever. So it can be used in a very large variety of applications. So basically, here we have some customers and we have potential sites for plans, and we're concerned about two things: the fixed cost of opening a facility, which has a capacity also for handling customers, and we have transportation costs between the customers and the plants. And basically, the objective here is to minimize the sum of the infrastructure costs, so the total fixed cost of the open facilities, and the transportation costs from the customers to the plants, or the other way around. It doesn't really matter. Okay, so if you're allergic to mathematics, don't look at this one. So this is the mathematical formulation of this. I don't expect anybody to be able to pass a quiz on this at the end of the webinar. But the thing which is important, this is a mixed integer programming problem, and the one thing which is really important for our discussion is to notice that we have two types of variables. We have at the bottom those Xij variables. Those correspond to flows that will exist between the customers and the facilities, and we have Yij variables, which are combinatorial. They just tell us whether plant J is open. And why do we want to do this? Well, the one thing is that if I know the values of Y, then I can derive optimal flow variables, values for the flow variables, by solving a very simple linear programming problem, which is something which can be done very effectively. And so if I were to tell someone this is the optimal location vector, Y star, and then we can retrieve the complete solution to the problem. So this is useful. Also, we can argue about the properties of this mathematical programming problem. And so this is for those who are mathematically inclined, is in fact we can say something that by just looking at some mathematical set, the polyhedron of feasible flow vectors, I know that the optimal solution, I can retrieve the optimal solution of the overall problem by looking at those flows. Okay, so the other details are not really important. Okay, so why do we do this? Well, why am I bringing this to your attention? Well, I just want you to be aware that I have this big complex problem where I have flow variables X, location variables Y, and obviously I could do a search on the full space. On the other hand, I could just look at the search space defined by the location variables. Or I could look at another set, which would be the set of extreme point of feasible flow vectors. And if I do this, I can define neighborhoods for this problem that are quite different. And those neighborhoods will depend upon the search space chosen. For example, if I'm looking at the location variables, we have a whole host of neighborhoods that have to do with opening or closing a facility or swapping the location of a facility. On the other hand, if we're looking at the flow variables, well, then it's much more technical, but we can use, in fact, some operations in the solution of the linear programming formulation, and we can define neighborhoods that are related to this. So lot less immediate, but can be extremely effective. And in fact, I won't be coming back so much on this. In fact, we have worked back in the 1990s on the Metaheuristics for network design problems that were using, in fact, both of those types of neighborhoods, and they have completely different, I would say, characteristics and performance. Okay, now that we've just come with this, I would say, beginning of, I just wanted to do this so that you're aware that things are not so trivial. Okay, let's talk about trajectory-based method. The first one is called simple local search. It's not really a meta-heuristic. It's just really the simplest of all trajectory-based methods. It's related to the iterative improvement methods that I described before. One would just create an initial solution and improve it using a single neighborhood structure, and this will stop when a local optimum is encountered. In fact, there are two variants of this. The first one is called best improvement, which means that whenever you're at the solution S, you will just look at the complete neighborhood of S and then take the best solution in that neighborhood. The second variant is called first improvement, means that you start evaluating neighbors, and the moment you find an improving one, you move to that new neighbor. And it's not clear, even though this thing has been used for many, many years, it's not clear which one is the most effective. It depends on the problem. Then we can extend this in a pretty simple, well, I would say natural way by just in fact, considering different initial solutions. So the idea would be just to generate a number of initial solutions and just apply the local search scheme, and then retaining the best of the solutions that are found. So again, a pretty trivial heuristic. Now, let's go back to simulated annealing, which caused such a splash in 1983. So what is this? It's in fact, it's kind of local search heuristic, but it's probabilistic in a sense that it will look at a neighborhood and then it will select randomly a solution in that neighborhood. And I'll tell you a little bit more on the next slide. So what is important about simulated annealing is that it's able to overcome local optima, and it does have some convergence properties. And I would say that this is the first of a long list of methods which are based on some analogy with the real world. Here, the analogy has to do with the cooling of material, metallic material in a heat bath. And the way the analogy works is that solutions correspond to configurations of particles in that metal, and usually it's kind of a crystal. And the objective function corresponds to the energy of the system, and the idea is that finding a minimum objective function is like looking for a minimum energy configuration. The method uses the so-called Metropolis algorithm, which is a method for simulating, in fact, the annealing process. And the best way to look at it is as a controlled random walk in the space of solutions. So as I said, from a current solution, one generates a new candidate, and if the move improves the objective function, then it is accepted. That is, the current solution becomes the new point that has been generated. On the other hand, when the move deteriorates the objective function, then it is accepted with a probability. And the probability, it depends on two things. The first one is the amount of degradation, so how bad this solution is compared to the previous one. And also on a parameter which is called temperature, and this is a parameter that is adjusted as time goes on in the operation of the algorithm. So at first, temperature is high, and lots of degradation will be accepted, and as time goes on, it becomes lower and the criteria are stricter. This simulated annealing approach has been, in fact, extended and generalized in a number of ways, and something which is kind of funny is there is this those methods that are called deterministic annealing, which is more like local search. As local search, I look at a neighborhood, and then the question is, if I take, for example, the best solution in the neighborhood, the question is whether we will accept deterioration of the objective function. And this is done up to a threshold. And again, the threshold will decrease as the algorithm progresses, so eventually the algorithm will stop. Another method is a thing called variable neighborhood search. This is something that was introduced by some colleagues in Montreal, Pierre Hansen and Nenad Mladenovich, back in 1997. And the idea is very natural. It has to do with, instead of using a single neighborhood in a local search framework, one could use several in some predefined sequences. And in fact, over time, variable neighborhood search has become quite a complicated method. It has some of its variants are extremely complicated, and I would not try even to explain this to you. I'm not sure I even understand myself. But there's one which is very simple and very natural, which is called variable neighborhood descent, which is quite nice. It's just a multi-neighborhood extension of local search, and it just amounts to first performing local search with a first neighborhood structure. When a local optimum is encountered, switching to another neighborhood structure, pursuing local search, and then eventually to a third neighborhood, and so on, in some kind of circular fashion. And one of the neat things about this is that, oops, I think I just realized I did not put the second slide there. One of the neat things is that the whole method will stop when a point or a solution, which is a local optimum with respect to all the neighborhoods considered, is encountered. So it's usually a much, much, much better solution than if we would have been looking at just one of those neighborhoods. Now, let me tell you about taboo search. So we're back in the, in fact, late 80s, late 70s, early 80s. In fact, the method was formally introduced as taboo search in, well, 1985, 1986. In fact, there's a Glover paper of 1985, which has not been widely distributed, which introduces the term. In fact, I would say the primitive version of the method was in fact described in a 1977 paper, but the method really appeared in 1986. Then Pierre Hansen also proposed in 1986 a method which he called steepest ascent, mildest descent, which has a number of similarities with taboo search. The general concept of taboo search is that it is metaheuristic, so it controls some inner heuristic which is tailored to the problem at hand. It relies on a number of artificial intelligence concepts, mainly through the idea of maintaining memories. In fact, we will want to maintain a history of the search in those memories. And the key idea is that one will allow some non-improving moves in order to be able to overcome local optima. So in fact, when a local search method runs into a local optimum, it stops. In the framework of taboo search, it just keeps on looking at other solutions. However, by doing this, it creates a situation that it can cycle. So I'm looking at solution A, which is a local optimum. Then I'm going to modify it, move to solution B. But when I am in B, there's a very high, well, normally A is in the neighborhood of B. And from B, there's a very high possibility that the search will move back to A. And then it would just start to ping pong between A and B. So how can this type of behavior be avoided? Well, the idea is just to keep a history of the searching process so that we can remember where we have been and that we can prohibit coming back to previous solutions. And this is the whole notion of taboo moves. Well, how those taboos are working? Well, generally taboos should be looked at as a short-term memory of the search. And short-term because normally one only wants to record a fixed, and I should say limited amount of information. What are the possibilities? Well, one natural possibility would be just to record the last solutions that have been encountered, so the last current solutions. Well, this is pretty expensive and it's used only very seldom. It is used, however, by some authors. What is more usual is to record the last modifications performed on current solutions and to prohibit reverse modifications. And I'll show you examples of this. And the final version also would be to record key characteristics of the solutions or the transformations. So some examples. So going back to our vehicle routing example, suppose that I'm using a local search neighborhood in which what I'm doing is I'm just moving one customer at a time from a route to another. So I'm moving customer I from a route R prime to a route R second. So what can I do with respect to taboos? Well, there are several possibilities. One would be just to forbid the reverse move, and we would just record the triplet I, R second, R prime, and we know that if we have this in our memory, it means do not move back I from R second to R prime. Those type of taboos are very precise, but they're not very powerful. Sometimes it's better to just forbid all the moves that would bring back the customer in its original route. So we don't want to send back I to route R prime, and then we just have the pair I, R prime. And a final alternative, which is pretty blunt, would be just to say, okay, we don't want to touch customer I for some time. So those are a number of possibilities. If we go into more detail on those taboos, well, one thing is we could use multiple taboo lists. So we can record different types of information about the moves. They are easy ways of implementing, I would say, straightforward taboos. However, what has been shown, and this has been shown like many years ago, it's been shown like more than 20 years ago, is that fixed length taboo lists will not always prevent cycling. And there's been a number of other possibilities to overcome this. For example, we have used so-called random taboo tags, where in fact the duration of this, I would say, of the number of iterations during which a taboo is effective is selected at random, and or we can just activate taboos in a random fashion, but this has not been used very often. Now, one big concern about those taboos is that they might prove to be too powerful, and they will in fact discourage attractive moves. And because of that, people have been forced to invent a device that can cancel taboos, which is called aspiration criteria. And the key thing there is we just want to make sure that we cannot cycle. And one way of ensuring this is, for example, if we're considering a solution that should be taboo, but the value, the objective function value for this solution is better than any solution that we've seen up to this point, well, we know we're not cycling and we should not really apply the taboo. So here is what I call a template for simple or basic taboo search. So I'm just trying to maximize a function. S is the current solution. S star is the best solution that we've seen up to a point. F star is its value. The taboo list is called T, and N of S denotes the neighborhood of S, and N bar of S is the admissible subset of N of S. And so the whole method starts with a very simple initialization, which is to construct some initial solution S0, as in any local search scheme, and then to set S and S star to be equal to this best known initial solution. F star is the value associated with S0, and the taboo list is empty. And the search process itself is very simple. Is as long as the termination criterion is not satisfied, we just take the best S prime in the neighborhood N bar of S, the non-taboo neighborhood of S, and this becomes the new current solution. And then if the value associated with this new solution is better than the best value we have recorded, then we just record the fact that this is a new best solution, and we update taboos. So what about termination criteria? Well, termination criteria, if we just don't take special action, the taboo search could run forever. So in practice, the search is stopped usually after some number of iterations, sometimes after a number of iterations without improvement in the best objective value, so no improvement in F star, or sometimes when the objective reaches some pre-specified threshold value. Also, in the most complex implementation of taboo search, normally what we will do is we will have a number of phases, and each phase will be controlled by such termination criteria. Okay, probabilistic taboo search. One thing that has been noticed is that in complex problems, the neighborhood can be extremely large and take a very long time to look at. So one way of alleviating this is just by sampling part of the neighborhood, and this has two advantages. It reduces computing times, and also it works as some kind of anti-cycling device, but one has to be careful because one could miss the optimal solution, and there are special caveats to use if one is implementing this, but I don't think I have time to go into the details. Okay, now I'm going to tell you about two very important concepts in taboo search. I would say two fundamental concepts. The first one is search intensification. So the idea here is to try to mimic the behavior of an intelligent person, in the sense that we would like to explore more thoroughly portions of a search space that we believe are promising. So from time to time, one will stop the normal search process and start an intensification phase. Usually this is based on some kind of intermediate term memory, And one type of memory that we use for that is so-called recency memory. So we're just recording the number of iterations that some elements have been present in the solution. Okay, what do we mean here? Well, we want to know, for example, how many times the plant at location 15 has been open. Maybe we've had this plant open in a large fraction of the solutions. And what do we want to do? Well, maybe we would like to just make sure that the plant at location 15 is open. So very often what we're going to be doing is to restarting the search from the best known solution encountered so far, and then maybe fix some good elements in the solution. We could also change the sample size if we're doing probabilistic taboo search, or we could switch to a more powerful inner heuristic to be looking, in fact, at a more, let's say, do a more effective search around this best known solution. The converse of search intensification is called search diversification, and if you ever intend to implement any taboo search method, this is the most important concept in taboo search. So one of the problems of taboo search is, like all local search methods, the normal searching process tends to be, in a sense, too local. It will focus on some area of the search space, and it will not look at solutions that are drastically different from, let's say, the initial solution that was fed to the method. And when this happens, one can end up being very far from the optimal solution. So diversification is a mechanism that has been developed to force the search in those previously unexplored areas. How is it done usually? Well, it's based on what we call frequency, long-term memory, frequency memory, which will record the total number that each element has appeared in the solution. So, for example, I know that since we have performed 1,000 of iterations since the beginning of the search, and there has never been a plant in location 27. So maybe we would like to see what happens if we have a plant open in location 27. So the most common diversification techniques are what we call restart diversification. So here we're going to be forcing unfrequent elements in the solution, and we will just restart the search from this new solution. There's also another device which is called continuous diversification, which is, in fact, just adding a term in the evaluation of move that accounts for element frequencies. And there's also a thing which is called strategic oscillation, which will be described not in the next transparency, in the second next transparency. Okay, because now I'd like to turn to one thing which is a source of concern when applying local trajectory-based method, which is how can one handle constraints? There are many cases where accounting for all problem constraints in the definition of the search space doesn't really make sense. And in fact, what people do is they relax those constraints. They would relax some of the constraints, and this has a number of beneficial impacts in a sense that the wider search space can be easier to handle, and maybe we can use much simpler neighborhoods. And when this is done, then what is usually the best way to deal with this is by adding constraint, a weighted penalty term to account for constraint violations in the objective. Now, the big issue I just realized that here, in fact, I just forgot to copy the proper material. Okay, the big issue is that if this happens, we have to find a way of finding the proper weights. And the proper weights can be done using so-called self-adjusting penalties by, in fact, looking at the history of the search and trying to balance feasible and infeasible solutions. And in fact, one thing we can do is we can induce diversification by playing with the weights, and this is what is called strategic oscillation. Okay, so that's basically what I wanted to say about trajectory-based methods. Let's move to population-based methods, and I just would like to reassure you this is much shorter than the part on trajectory-based methods. So, okay. So I told you already that genetic algorithms were defined first by Holland back in 1975. So before Metaheuristics, the Metaheuristic concept existed. And what are genetic algorithms? It's a search method that in fact replicates the evolution of a population of solutions along lines that mimic the Darwinian evolution principle. So it's survival of the fittest. So genetic algorithms are based on this concept of fitness, and fitness really is the higher fitness are the solutions that are best with respect to the objective function. So in this world, solutions, and in fact implicitly the search space, they are encoded as so-called chromosomes. And in the first implementation of GA, those were always encoded as bit strings. So it would be a bit string representation of the problem solutions. Later on, it was found out that in fact it's a lot more effective to use, in most cases, to use natural encoding of the solution, so a way to describe the solution. So for example, if I'm looking at the traveling salesman problem, a natural way to encode the solution is just a sequence of cities that the salesman will visit, and it's just a permutation of numbers. Now, they are also, if one looks at recent implementations, there are sometimes very clever encoding schemes. And for example, my colleague Christian Prince proposed a pretty interesting approach for vehicle routing problems. Unfortunately, we don't have time to go into all details of this now. So the way genetic algorithms work, they are I would say at the core of any genetic algorithms, two main operators that operate on solution. The first one is called crossover, and here I give you an example of a so-called one-point crossover. So I have solutions that are encoded as sequences of 8 bits. So the first solution, which is 100111111, and the second solution, which is 01010001. And what we want to do is from those two solutions, we want to create offspring. In fact, the one-point crossover allows us to create two offspring from two parent solutions. So here, if I cut after the 5th bit, the first offspring will have the same first 5 bits as the top parent and the last 3 bits of the bottom parent, and it's going to be the other way around for the second offspring. So this is a way of mixing, I would say, elements of solutions. The second operator is really mutation, and this is just changing with some probability the value of one gene. So here I have binary representations. So what I would do is I would just draw a random number to select one of the bits, and I would just change its value from 0 to 1 or 1 to 0. Typically, genetic algorithm is run for a number of what we call generations, in fact, could say iterations. And in each iteration, the process starts by selection. So one will select some individuals, and the selection process is biased towards the fittest individual, so the best one in the population. And then those individuals which have been selected to reproduce will have the crossover operator applied to them to generate new offspring. Then mutation will be applied to the offspring, and the resulting individuals will be added to the population. So there are many ways. We could have a complete replacement of the population, or we could just be replacing some less fit individuals. Now, some of the conclusions that have emerged over time is that bit string encoding is not really appropriate for many combinatorial problems. And this is because crossover may lead to either infeasible or meaningless solutions. And also, pure GAs are not very good at solving hard combinatorial problems. So that, in fact, people have been using hybrid GAs, or some people sometimes call those methods mimetic algorithms, by using some form as local search, usually as a replacement for the mutation operator. Another category of methods, evolutionary algorithms, which are some kind of extension or generalization of GAs, and which include also strategy parameters in the solution vector. Then another technique called scatter search, in which a number of solutions are recombined using linear operators. So for combinatorial problems, that is not that good because one needs to define some rounding processes to get integer solutions. Then let me tell you briefly about ant colony optimization. So this is something that was proposed in the early 90s by Colorni, Dorigo, and Magnizzo. And again, this stems from an analogy with a real process. In fact, the way colonies of ants forage for food. So ants will, when they forage for food, they deposit what we call pheromone on the path between the food source and their nest. And the quantity of pheromone normally depends on the quality of the food, the distance, and the number of ants traveling over the path. So the analogy is really to equate the value of a solution with the quality of food and the distance in the real world with the cost of individual elements leading to a good solution. And in the method, artificial pheromone is, quote unquote, added to modify the cost of individual elements that lead to good solution. So what happens is that in the method, artificial ants will repeatedly construct solution using those modified costs, which are just dynamically adjusted until some point where it's thought that some interesting solution has been found. Now, after a while, people that have been using those methods have realized that if we just use ant colony optimization by itself, they have a hard time producing good solutions for hard combinatorial problems. And in fact, one must include local search steps to be able to find to be really effective. Okay, a brief rundown of some recent trends in Metaheuristics. Well, one thing, a resort to parallel processing, either to alleviate computationally demanding steps of methods, and like, for example, taboo search, or higher level parallelization by having different search threads exploring a search space in parallel and exchanging information. And for those that are interested in this, I strongly recommend a book that's been edited by Enrique Alba, but which is now a bit old. It's 2005. Something even more popular than parallel methods is hybrid approaches. And the idea here is to combine the strengths of different metaheuristics and alleviate their weaknesses. There's even been combinations with exact methods, and this has led to, in many cases, so-called Metroheuristics. And those hybrid approaches can be classified under two schemes, what I call unified architecture. So here we have a single algorithm in which steps, I'd say, coming from different methods are combined in a single stream, single flow of operations. And something which is also quite interesting, parallel hybrid. So here, combining parallel processing and hybridization ideas where, in fact, one could have different, I think, can almost say agent or processes that are running pure implementation of standard metaheuristics. So, for example, many years ago, we developed a hybrid like that in which we had one genetic algorithm process running in parallel with 4 taboo search processes, and this proved extremely effective. Now, this might be of interest to several of you, is one thing also about metaheuristics is they've been moving over time to, I would say, non-traditional application areas, so more general forms of mathematical programming. In some cases, moving away from discrete problem to consider continuous optimization problem. And this includes also multi-criteria optimization. And in fact, even implementations of multi-criteria optimization on for problems with continuous decision variables. Some work related to stochastic problems and also real-time decision problems. And in fact, metaheuristics have been applied. There's a long history of application of metaheuristics to real-time management problems. So, for example, we've been applying taboo search to real-time, to managing in real-time fleets of vehicles for different types of application. Now, just a few words about some recent work. that we've been doing, the so-called unified hybrid genetic search. This is an approach that has been proposed by a former PhD student, Thibaut Vidal, and his co-supervisors. But I must say that 90% of the credit would go really to Thibaut Vidal. And the idea here is to have a population-based method, but with a clever technique for creating offspring, to have a very important local search component. And one of the key ideas of this method is the idea of bias fitness. And here bias fitness means that we're looking at a performance metric for solutions that includes both a quality part and a diversity part. So in fact, the whole concern about diversification is just injected directly into this bias fitness. And this idea can be used for any kind of combinatorial optimization problem if somebody is using kind of a method related to genetic algorithms. And it turns out that this method has been performing extremely well with low running times. And in fact, many of the solutions that have been found with this method in short computing times have later been shown to be optimal using much more demanding exact solution methods. Okay, conclusion, because I've run out of time. I hope, I'm not sure, but I hope that I've been able to convince you that metaheuristics are very effective approaches for tackling difficult combinatorial optimization problems. But I'd like to stress the fact that they're not a panacea. And in fact, people believe that just because they're implementing a metaheuristic, they will have an effective solution method, are usually dead wrong. And this is...
Great. Thank you, Michel, for a very stimulating and informative talk. That was excellent. So I'll open the floor for questions. I know we have one question from Ken Kiaki at the PSC. Ken, do you want to say your question, or do you want me to read it on the chat window? I'll take silence as you want me to read it from the chat window. So are natural problems that the genetic and ant colony methods based on, he responded and moved the thing out of my window. Hang on a second. Are the natural problems that the genetic and ant colony methods are based on easier than the hard problems people are trying to solve, or is there something we're missing in the application of the former to the latter? For example, do you think it's possible that real evolution has a local search element built into it?
Oh, this has been a really hard debate in GA circles, and sometimes people who use local search component in GAs are sometimes ostracized for being Lamarckian. Some people saying that the real genetics are work under Darwinian dynamics. Although I think this would need to be requalified, because if you look at some recent progress in biology, it's not clear that there's not some adaptation going on. But my idea is that the fact that real nature makes progress using Darwinian dynamics, and which are pretty different from, I would say, what we'll find with hybrid genetic algorithms, is, in a sense, it's irrelevant, because I mean, Darwinian evolution modeling is descriptive, it's not prescriptive. Here we're just trying to solve combinatorial optimization problems. And for this, we know that having local search helps tremendously.
Okay, great, thanks. I know, Lorette, you had a question that you wanted to ask?
Yes, first I do want to thank you a lot, Michel, for an excellent presentation that for me really achieved what this seminar is about, in the sense that we will not be able to address in a more complex manner in our real world problem where many of us are operating at a substantive level until we understand a bit better the actual decision support or optimization of the type of model that you are talking about. So thank you very much for that. I have two questions. One, when you talk about multi-criteria and you talk about all this optimization is for the production function, I'd like to hear a bit more how you actually integrate those multi-criteria when sometime, like in the context of food systems that have been getting Sean and I together, is that it is kind of believed that if you optimize the cost and you are kind of having a positive effect on the health side. That's my first question. Second question is that I was very interested in all the way, because when I did my PhD at Cornell, that was the time that behavioral economics and heuristic and so on were coming through with Danny Kahneman, Amos Tversky, and Dick Taylor. And what I was very interested in here, observing here, is that in many ways your heuristic in the work you do are very much like the behavioral heuristic that we were talking about. What seems to have been evolved further is that in the behavioral heuristic, two things. One, they have been and remain descriptive without being linked to optimization or to kind of trying to move toward kind of some optimal solution of some sort, whereas on the behavioral side, it was opposing the economist pure ideal vs descriptive. So I'd like to hear what you have to say in terms of to what extent this meta-heuristic that is in some way saying, let's control this portfolio or account for this portfolio of heuristic, and let's try to get some solution that is moving us toward optimization vis-a-vis remaining within the descriptive sphere. When we started this Brain to Society in 2006 or 5, I had John Holland with us at the same time as I was all the behavioral people. And John was talking about his famous algorithm about the flock, the bird's flock. And we are still very much on the behavioral side at a metaphor understanding, in my view, about integrating that complexity. So if you could address those two questions as shortly and simply as you can. I'm very aware that we could spend the whole day debating each of them. So back to you, Michel.
Okay, with respect to the first question, I must say that multi-criteria meta-heuristics are, in a sense, in a different ballgame. If only, you know, all that I presented is centered around the idea that we have a single function, f of x, that we're trying to optimize. And the question with those multi-criteria optimization is that we have at least two functions. And basically what we have to do when we're dealing with them is to really look at the different criteria at the same time and try to, so what is done is usually, it's fairly easy for by criteria optimization. If we have more criteria, it becomes a lot more complicated. But for by criteria optimization is that we just try to build, as time goes on, some kind of pseudo Pareto front by recording non-dominated solutions. So the method will still, let's say we're doing taboo search. So it will still look at a current solution. From this current solution, it will look at different points. There's going to be a rule for moving the current solution to one of the neighbors. And it's a bit different because here we don't have just one objective, but also as we are looking at the value of solutions, we want to compare those not to the best solution, but with what we have in our Pareto front information structure. So we need to maintain a whole data structure that contains this. It's not the real Pareto front, but let's say pseudo Pareto front, and we need to update this as one goes along. So it's the general mechanics of the method are not that much different, but somehow there's a really the need for a special effort targeted at the multi-criteria nature of the whole thing. So that's I would say for the first one. Regarding the second question, well, this is the whole question about those I would say normative versus descriptive heuristics. It's clear that the intention is different. It's and I know some of those descriptive heuristics, for example, those kind of cell transmission format and other type of things like that. And I think the one thing which is really important is is how much the intent is different. And it's the whole purpose, and it goes to the same thing when we were talking about genetic algorithms. There's the whole thing about descriptive and prescriptive methods or models. Is when we're looking at the descriptive things, we're just trying to be as close as possible to what happens. And when we're going at the prescriptive, is we have some target optimal solution that we want to find, and the idea is to try to do this as effectively as possible. I don't know if this answers your question.
Yeah, no, very much. Thank you. Thank you. I see that we are already 5 minutes after. But this is a conversation, Michel, that we will continue for a long period of time over the upcoming year. Back to you, Sean.
Okay, great. Well, yeah, I think we're out of time. So I want to again thank Michel for a very wonderful talk, and we'll be announcing on the email our next bridge webinar, which, do we have a date for that yet, Laurette?
Yeah, for now. In fact, almost every 2 weeks we have some in the coming. It's Jean-Pierre Dubé from Chicago on October 19th, bringing empirical and analytical modeling of food retail data in terms of moving toward both informing retail and manufacturing decision making, as well as policy implication from the health side. Okay.
Great. Well, cool. So we will hopefully see you all there. And again, thank you very much, Michel.
Yeah, I have maybe one last remark to make, which is that I don't know if people can capture the slides from when they are connected, but the one thing is that I'm definitely ready to make the slides available, but then I noticed that there's one slide where I don't know exactly what I did. I know that I think I just deleted the wrong slide when I was. I'd like to make that correction and to send this back to Sean, and then if people want to get them, they could get them from Sean.
That would be great.
Okay, I'll do this within 10 minutes.
Okay, great. Thank you.
Thank you, everybody.
Okay, bye.